Hey everyone, and welcome! Today, we're diving into a concept that is the absolute bedrock of all of calculus, continuity. Now, if that sounds a little intimidating, don't even worry about it, because I'm going to give you a simple, super powerful checklist that's going to make you a master. Let's get right into it.
It all boils down to a really simple question. If you can take a pencil and trace a function's graph without ever lifting that pencil off the paper, then you've basically got the core idea of continuity down. It's just a smooth, unbroken line. The real challenge, though, is how do we prove this with math?
So, here's our game plan. We'll start with that intuitive pencil test. Then we'll build a formal checklist. After that, we'll look at what happens when things go wrong, and then we'll put it all into practice with some real examples. We'll even cover the common traps students fall into, and, maybe most importantly, why this whole idea is such a huge deal.
Okay, so let's start there. How do we take that simple idea, the no pencil lifting rule, and turn it into something real, something we can actually prove? We have to translate that gut feeling into the precise language of mathematics. And this right here is the key that unlocks everything. Seriously, think of this as your secret weapon, your diagnostic tool for any function you come across. It's a straightforward, three-step process that will tell you with 100% certainty if a function is continuous at any given point. All right, these are the three golden rules. First, the point itself has to actually exist, right? You can't be continuous at a spot that isn't even on the graph. Second, the limit has to exist. And all that means is as you get super close to the point from both the left and the right, you are heading toward the exact same y value. And third, this is the most important one. The value you're heading towards, the limit, has to be the exact same value you land on. If even one of these fails, it's a no-go. All three have to pass, no exceptions.
So, what happens when a function fails our test? Well, this is where it gets interesting, because how it fails tells us exactly what kind of problem we're looking at. Each broken rule points to a very specific type of break in the graph. Let's look at the different diagnoses.
This is why our checklist is so powerful. Each failure tells a story. If the limit exists, meaning you're heading to a specific spot, but the point itself is missing, that's a removable discontinuity. Just think of it like a tiny hole in the road that you could easily patch. If the graph literally jumps from one y value to another, that's a jump discontinuity. And if the function just shoots off towards positive or negative infinity, well, that's an infinite discontinuity, which you probably already know as a vertical asymptote. All right, enough with the theory. The best way to really get this is to see it in action. Let's get our hands dirty and run through three different examples, starting easy and working our way up to a trickier one.
First up, we've got a classic polynomial function. Now, intuitively, we all know what a parabola looks like. It's a smooth, unbroken curve. But let's not just trust our gut, let's prove it with the checklist at the specific point x equals 2.
Okay, let's run the diagnostics. Step 1, does f of 2 exist? Yep, we just plug in 2 and we get 5. So, check. Step 2, does the limit exist? Well, as x gets closer and closer to 2, the function gets closer and closer to 5. Check. And finally, step 3, do they match? Yes, 5 equals 5. It passes all three tests with flying colors. And there you have it. Because all three conditions were met, we've just mathematically proven that this function is continuous at x equals 2. No question about it. Okay, now for something a little more fun, a rational function. And right away, you should see a red flag. If we try to plug in x equals 1, we're going to get a 0 in the denominator, and that's always trouble. Let's see what our checklist says. And boom, we hit a wall right on step 1. f of 1 gives us 0 over 0, which is undefined, so that's an immediate fail. But hold on, let's check the limit anyway just to see what's happening. If you factor the numerator, you'll see we can cancel out that problematic x minus 1 term. And when we do that, we find the limit is actually 2. So the limit exists even though the point itself doesn't. So here's the takeaway. Since condition 1 failed, but condition 2 passed, our diagnostic table tells us exactly what this is. It's a removable discontinuity. All that means is there's a tiny, single-point hole in the graph, right at x equals 1. All right, time for the final boss, the piecewise function. These are the functions that play by different rules on different parts of the graph. The only spot where continuity might be a problem is right at that transition point, in this case, at x equals 2. Okay, let's run the checklist. Step 1, does f of 2 exist? Yes, it does. The second rule there applies when x is greater than or equal to 2. So f of 2 is just 5. That's a check. But now for step 2, the limit.
Remember, with piecewise functions, you have to check from both sides. As we approach 2 from the left, we use the top rule, x plus 1, so the limit is 3. But as we approach from the right, we use the bottom rule, so the limit is 5. Since 3 does not equal 5, the overall limit does not exist, and that is a hard fail.
And that right there is a perfect example of a jump discontinuity. Our checklist failed on the second condition because the left-hand limit and the right-hand limit just didn't agree. The graph literally jumps from one value, down at 3, up to 5 at that breaking point.
Okay, so you've got the tool, you've seen it work. Now I want to make sure you don't get caught by some of the common traps. These are the little mistakes that are easy to make, but you'll be able to spot them from a mile away.
Here is the biggest myth out there. So many people see a piecewise function and they just automatically assume it has to have a break in it. But that is absolutely not true. If the different pieces of the function are designed to meet up perfectly at that transition point, the function can be totally, completely continuous.
So, to recap those pitfalls, just remember, you have to check all 3 conditions every single time. Don't just stop at the limit because you might miss a hole in the graph. And never ever assume a piecewise function has a break. Make it prove itself with the checklist.
So, after all this, why do we even care so much? I mean, beyond just passing a test. The thing is, continuity is what we call a gatekeeper concept. It unlocks some of the most powerful and honestly elegant ideas in all of mathematics.
And this right here is the big payoff. It's called the intermediate value theorem. It sounds fancy, but it says something incredibly powerful and intuitive. If you have a continuous function, an unbroken line, over some interval, then you are guaranteed that the function has to hit every single y value between its starting point and its ending point. There are no gaps, no jumps, no missing values, period.
Now just think about what that means for a second. It means if you have a continuous function that's negative at one point and then positive at another point, you are guaranteed that it had to have crossed the x-axis somewhere in between. It guarantees a solution exists. This is a fundamental tool for everyone from mathematicians to engineers trying to solve real-world problems.
And really, that's what makes this whole thing so cool. Continuity isn't just some random rule you have to memorize. It's a promise. It's a guarantee from the universe of mathematics. And it makes you wonder, if knowing a function is continuous gives us this much power, what other incredible guarantees are just waiting to be discovered inside the language of math?